Good. Now we're going to get started. So thanks everyone for coming. I have just a few announcements before I introduce Vincent and we get started with the talk. The first is that we'll be passing around a sign-up sheet. If you wouldn't mind listing your name here, this helps us with our funding agencies, our sponsors. I'd like to thank sponsors of the Toronto Vision Seminar, Google DeepMind, Fields Institute, and Faculty of Arts and Science, who allow us to bring in these great speakers and host these events. And then we'll also we'll be taking a few photos as well to put up on our webpage. If you don't want to be included in the photos, you can come up to us afterwards, so just let us know. Okay, and so it's also my great pleasure to introduce Vincent Sitzmann. Vincent's an assistant professor at MIT, where he leads the scene representation group. He did his PhD at Stanford University, postdoc at MIT. We actually did our PhDs together, so I've known Vincent for a while, and we kind of grew up in our academic careers together. So it's really a pleasure to host Vincent. And Vincent's done some really amazing and influential and seminal work, I would say, in computer vision, and representation learning. So please join me in giving a warm welcome to
David, it's a pleasure to be here, and yeah, to visit David again and to see so many familiar faces. It's really a beautiful place and a beautiful university. So my talk is going to be about learning to model the world and yourself from vision. I hope we get through all of it. I definitely have too many slides. You'll see how we navigate it. Okay, so let's start with motivation. That's always good. And this is actually a slide that I made for my PhD thesis defense, which David visited. So like, literally, this is the same slide. And of course, today I would make some things differently, but the interesting thing is many things kind of are the same. So my motivation has always been to ask, there's all of these different applications of computer science, right? There's robotic manipulation, robotic grasping is what I called it back then. Then we have graphics, right? Which is like, of course, photorealistic rendering, physics simulation, then we have autonomous navigation and planning, and then the other things maybe don't look at them. So the thing is that I want you to think about is what do all of these different applications have in common? And what they all have in common is that they all require some model of the underlying world, right? So in manipulation, that's obvious, right? You have your laptop on your lap. Think for a moment and appreciate what your brain knows about that laptop and what it allows you to do to manipulate that laptop, right? You have an understanding not only of the geometry, of the color, of the material, how heavy it will be, blah, 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 right? So clearly, manipulation requires a model of the world. Graphics, of course, the same. We need some model of the underlying scene before we can render it photorealistically. And light transport is, of course, also a physical process. Physics simulation, I think that's self-explanatory. Autonomous navigation, same. We need a model not only of how our car will behave, how other participants behave, etc. So all of this requires some kind of model of the underlying world. And today we would call that a world model. Today, interestingly, still today, most of these different applications have entirely different handcrafted representations of the world, right? In graphics, this is obvious. Graphics, we have like meshes, and then we have like handcrafted renderers on top of them. In robotic manipulation, this is kind of changing, but nevertheless, right, lots of it is still based on, point cloud segmentation, planning, etc. Then in physics simulation, of course, the same. We have like custom crafted representations to like be able to do finite element simulation, etc. Okay, and the interesting thing, however, is right that this is, of course, something that's unsatisfying, and it also makes these different things kind of brittle, right? There's like lots of things you can't handcraft into these representations. That's only things that you already know that you can endow these models with, etc., etc. And the thing that is striking is you can do all of these things to varying degrees with one model of the world, right? The same model that you have in your head that allows you to like think about, allows you to learn how to manipulate things is the thing that allows you to learn how to drive a car, or like learn how to imagine like different lighting conditions, etc. So this is kind of the goal of my research and has always been the goal of my research. I want to find ways in which we can learn models of the world, self-supervised from data that allow us to like then apply them to all of these different applications of computer vision. Okay, so interestingly, what do we have a shot at doing this today? Right? Like what has changed? Something that has changed is three trends. There's three trends that are coming together that allow us, I think, for the first time to make a significant dent in this problem. The first one is data, right? Of course, we have a lot of video data, needless to say, and for the first time, we can actually, also access the data and like process it at scale. But more so than just video, we have access to unprecedented amounts of robotics data of different modalities. Like there's really an explosion of data, and it's just getting more every day. We're deploying more robots, we're deploying more cars. this is going to just get better. We have a lot of observations of the world, so that's great. The second thing is, of course, compute. I don't need to say much about that. We have more and more compute. Even in academia, where we're a little compute constrained, we still have, actually significant amounts of compute. We have enough compute to train small video generative models, for instance, as we'll see later, and that's really fantastic. And then finally, of course, there's been this great breakthrough in techniques, and one of them certainly is the breakthrough in generative modeling. It's not the only one, but this is one we're going to talk about for the first part of the talk. So in generative modeling, we have, of course, large language models, and I think you are all familiar with large language models and the impact they have had. But then recently, there's also been this emergence of video generative models, right? And video generative models, if you see them deployed today, are still mostly kind of an entertainment kind of toy thing. Or if you look at Sora, right, it's mostly about I don't know, social networking is the thing. But that's not why they're interesting. Or maybe this is one reason why they're interesting, but there's many other reasons to be interested in them. In fact, the point that I want to make is that this you can think of as, right, a prototypical world model, which is it is a way of modeling and simulating the world, even though it's for now relatively rough, right? So let's talk a little bit about this. The first project that I want to talk about, and the first research project, that I really worked on in video generative modeling, is about realizing that there's these two different paradigms of sequence modeling. There's these two different paradigms of predicting the future. If you think about LLMs and if you think about video generative models, both of them fundamentally are sequence models. They are about, given the past, express a belief over the future. And that's, of course, kind of exactly what we need for our little world model. The thing that's interesting is, even though everyone says transformers are this big unifier and everything is just deep learning, actually the two paradigms we have used in the past to model these two sequences are dramatically different. On the right, you have LLMs, which are always trained with next token prediction. And then for video generative modeling, it's always video diffusion or full sequence diffusion. And the thing that is interesting is it's worth taking a closer look at those because they actually have different pros and cons. These two different paradigms of generating sequences have different benefits and disadvantages. We're not going to talk about all of them. I do want to point out the most obvious one, which is flexible horizon. If you go back to these things, to this video here, you will notice that when you interact with an LLM, it's not hard to just keep talking with it, right? It can basically stably generate very, very long sequences of text and keep generating text. If you look at the video on the left, you might already get the idea that maybe this is not true for the canonical way of training these video models. You can see that each of these is just a short clip, and I'm sure you haven't seen that many super long generated video models, although of course that is changing, and I think our work is maybe a reason why. Okay, so that's kind of the flexible horizon. There's clearly a difference in how we can roll out and generate arbitrary linked sequences with these two different kinds of models. And that's what I want to talk about today. I want to say, is there a way that we could get the best of both worlds from these two models? And some preliminaries for that. Who's familiar with diffusion modeling? I thought so. The second thing now is the idea of noises masking. So this is really kind of neat. And also very intuitive. Here's a little video sequence from the Minecraft. Adding noise to a sequence can be seen as destroying information and masking out parts of the sequence, right? So we can add a little bit of noise to these frames, destroy a little bit of information, or we can add all of the noise, in which case we have just masked out the frame. So it's kind of masked modeling, right? So the interesting thing is that if you use this kind of framework, you can actually look at autoregressive generation and full sequence diffusion in the same framework. Let me express both of them in this idea of masked sequence modeling. Let's start with autoregressive generation or next token prediction. For LLMs, you know how it works. The equivalent kind of for video generation kind of looks like that. Imagine we are starting to generate the first word, which in this case is just the first frame. It would look like image diffusion. Essentially, you start with noise and you train a model to just denoise the first frame. Now you have generated the first token, the first frame, right? Now we want to generate the next frame. And how do we do that in next token prediction? We assume that this thing that we just generated is a ground truth frame. And now conditioned on that, we're denoising the next frame, right? So now we just keep that one fixed, and then we're denoising the next one. So it's kind of a conditional distribution over the second frame, conditional on the first one. And in that way, we can just keep rolling out the model, right? Nothing crazy about that. Now, the problem is if you do that for text, it works really well. If you do it for video, it looks something like this. Even on Minecraft, right? It's not that great. Okay, so what's happening here? So clearly, the problem is something that's a very classic problem, which has names or ways of fixing it, called teacher forcing, professor forcing, etc. But it doesn't really matter that much. The key thing to realize is what's happening at training time. The model is trained always with ground truth frames that it has seen. in the past. And then at test time, you're giving it frames that it has generated by itself. And the problem is that the frames that it has generated has tiny, tiny errors in them. And the problem now is that the model believes these frames to be ground truth, and then it rolls them out, and then it goes up. And there's lots of cool ways of dealing with this, like teacher forcing, or actually professor forcing, and kind of that's the inspiration for the data diffusion forcing. Okay, how could we fix this? First, let's talk about the other paradigm, which is full sequence video diffusion. As you can see here, these videos look pretty crisp. They look pretty good. How does this work? The way this works is you essentially treat your whole video, like a whole chunk of the video, as one image, essentially. You take a bunch of frames, you add a bunch of noise, and then you denoise all of them at the same time, and then you generate the whole sequence like that, right? Okay, we can just do that. Train a model to do that. We just kind of directly sampling from the joint distribution. And that works really well. However, one problem is, how do we extend the video? Like, let's say we generated the first 4 frames. How do we now generate the next 4 frames, or like the next 2 frames? One compelling thing might be to say, well, we're going to condition on these 2 frames. We now want to denoise these 2 frames. But notice that the training method that we used has never seen this combination of noise levels. In fact, if you try to do that with the same model that you just trained, it's not going to work so well. And unfortunately, if you now go and you could kind of train this model to do autoregressive sampling, then you run into the same problem that we just saw with autoregressive sampling. Okay. And then if you try to, there's still tricks which are called like reconstruction guidance and so on, with which you can kind of try to like sample consistent sequences. We're not going to talk about them. If you try to build a baseline like that, this is what was proposed in the original video diffusion paper. What you get is kind of sequences that aren't actually aligned. It'll just look like you're sampling these distinct sequences, and each of them are kind of jumping from one to the other. Okay, so here's a really simple idea. Full sequence diffusion, as we just discussed, it just denoises all of the frames at once. We proposed this method, which is called diffusion forcing, and diffusion forcing is a very simple idea. It is just the idea of training a model where you give it a random combination of noise levels for each frame. It's incredibly simple, right? So essentially what you're doing, instead of training the model to always denoise the same combination of noise levels, you're just going to give the model a random combination of noise levels for each frame. Does that make sense? Okay, so it's this incredibly simple idea. Why does this make sense? What does it change? The first thing that it changes is that you're essentially training the model, if you think about it for a little bit, to complete any subsequence of the training data set given any other subsequence of the training data set. So for instance, in this case, right, we are clearly conditioning the model on this clean frame, and we are asking it to generate this frame from scratch, right? Does that make sense? And of course, if you sample all the noise levels randomly at training time, you're going to give the model every possible combination of subsequences. And so you're in fact training the model on to complete every possible subsequence. The next thing that's interesting is that both the full sequence diffusion and the autoregressive sampling are special cases of this, right? As we just saw. Note that both of them are special cases. They're just 2 different kinds of noise schedules with which you denoise your sequence. And so in fact, you can basically put both of these frameworks into the same thing. So like, I guess the point that is interesting to think about here is that while this looks like it's a choice of the model that you're using to generate these sequences, you can also just see it as a choice of the kind of noise schedule that you're using. So you can have a transformer that denoises, that takes in all of these frames at once, and you can still use it to sample autoregressively by just you picking a different noise schedule. Does that make sense? Okay, good. But this is pretty neat. It also allows you to do something else. What does it buy you? Let's talk about the flexible horizon that I mentioned in the beginning. How could we get the best of both worlds? Well, as we discussed, you can think of doing autoregressive sampling like this, right? You train your model, and then at test time, you give it one frame, and you ask it to denoise these frames. Does that make sense? This is exactly the autoregressive sampling. You will have the same problem that if you try to roll out this model in time, it will quickly blow up. But now we gained a little special superpower, which is we can tell the model that the frames it has generated in the past are not, in fact, ground truth frames. They are not to be trusted, because those frames have a little bit of error. They're generated, there's a mismatch between training time and test time. At training time, they were ground truth frames, now they are generated frames. So very simple trick, what we can do is we can just, we can just add a little bit of noise to the frame that we have already generated. And it turns out that this stabilizes the autoregressive rollout significantly, simply because the model now, and you can formalize it a little bit more exactly what kinds of errors it can like fix in this way. But this is just a simple way of stabilizing the autoregressive rollout. This was indeed the motivation for diffusion forcing, although it ended up being useful in other contexts. But this is kind of the one that is, I think, most easy to appreciate. And then the difference is quite stark. So this is the full sequence diffusion model, which we discussed earlier. This is the autoregressive rollout. And then this is the autoregressive rollout with the stabilization trick that I just described to you. This model was trained to generate 16 Minecraft frames at the same time. And now you can roll it out for, I forgot how many, probably like 400 or 500 frames. Any questions so far? Yes.
So then it's not, you don't have an infinite horizon then. It's still limited.
Yeah, it still eventually will diverge. I think this is a problem that people have fixed by now. And I think a part of it is simply scale. So I think if you make the model bigger, eventually it just gets more stable. And I think there's other tricks related to diffusion forcing and like other methods that I've heard about that also help with this. But this model, in fact, if you keep rolling out a little longer, it will still diverge.
Sorry, in diffusion forcing, during training also, you give it the noisy, like slightly noisy input, or just during the testing?
At training time, you give it random noise levels for each frame.
Okay,
basically,
right.
Yeah, you give it the whole sequence, and then you just give it random noise levels for each frame. Okay, good. Let's move on. Okay, so this is kind of easy to appreciate. One thing you of course notice is that this still is like blurry Minecraft videos, which is like not that great. So like that's a little sad. And it still kind of diverges after some time, even though now the rollout is much longer than the training sequencing. And one thing I will just say, when I was in my PhD, I don't know if this is still true, we learned about RNNs. This is actually a convolutional RNN. This is a tiny model. It's really small. And I still remember being really fascinated by this question, like how could we train an RNN that then rolls out sequences longer than what it was trained on? And in my PhD, I attempted this, as maybe some of you have as well, and it never worked. And so now I was like, wow, that's cool. This is like an RNN. I kind of felt redeemed, full circle, back to my PhD. Okay, good. So this was led by my student Boyan, who unfortunately left us to OpenAI now. But my first graduating student, he's brilliant. So if you see him around, he's awesome. So skip the summary. Okay, so now here's another thing that diffusion forcing allows you to do, which is also a trick, is a kind of a superpower that you earn with this particular sampling scheme that we just discussed. Let me provide you some context. Who is familiar with classifier-free guidance in diffusion models? Okay, about like a solid 80%. Let me briefly talk about it anyways. Classifier-free guidance is kind of like a superpower that diffusion models give you to trade off the diversity of samples that you get with the quality of samples that you get. So you basically pay a price on that diversity, and in return, you get better samples. If you go on any website that generates images, if you use any image generative model, these models are always sampled with classifier-free guidance to ensure that the text prompt, the image is more in line with the text prompt. How does classifier-free guidance work? You essentially train a model as follows. You train the diffusion model. It takes a noisy frame as input. And then, this is like the conditioning input. You ask it to denoise that frame. And let's say you have a class for this frame, like an ImageNet class, let's say. Okay, actually, I realized this actually is not the best thing for classifier-free guidance. Imagine you had a class for this image. What you do is sometimes you give the diffusion model this additional conditioning variable, like the class of the image, and sometimes you don't. And so at training time, you randomly drop it out. You can binary drop out. And then at test time, here's something cool that you can do. Given this image, you once sample the diffusion model with the conditioning, and once you sample it without the conditioning. Okay? And now the idea of classifier-free guidance, quite brilliant, is to say, well, this kind of difference between those two denoised images is kind of like a direction that kind of controls how much we're conditioning on this frame. And so you can basically exacerbate this direction in the image space, and you will basically condition the model more on the class. Does this make sense? Great. Okay, and this is like a superpower in diffusion models, really increases sample quality. So here's a cool little insight. When you generate sequences, the past frames that you have generated are also nothing else than a conditioning variable. Right? You are literally denoising these future frames conditioned on past frames. And the natural question to ask is there a similar concept to classifier-free guidance where we can basically force the model to sample higher quality frames that are more consistent with the past frames that we have already generated? And the only kind of tricky thing is that as opposed to a class, the videos are like variable length. You might have variable lengths of sequences. And the other special thing is that as opposed to a class, they're really the same. They're really the same modality, right? You have frames and you're generating frames, and so maybe we can use this to our advantage. And it turns out we can use this to our advantage. And I'm going to skip this. Or maybe not. No, we'll skip it. Okay, so essentially what you end up doing is something very simple. Previously there were methods for conditioning on the past, which were a little hacky. Essentially what you do is you have, for instance, an encoder that takes the past frames and then gives you a single latent code, and then you kind of condition the denoising transformer on that latent code with like a variety of methods. But the weird thing is, right, of course, these conditioning frames are also just video frames. So your model is already operating on video frames. So let's forget about that. Let's throw that away. Instead, we're just going to treat the past as part of the window that we're denoising, right? So like now we have past frames and we have the frames that we're trying to denoise. We just treat them as one part of the signal. And now the trick is, right, with our noise as masking trick, it's a very natural thing to basically designate what is history, like what is the thing we want to condition on, and what is the thing that we want to generate. It's just just a difference of noise levels, right? So now diffusion forcing basically allows us to basically pull this conditioning into the transformer, and now we just feed the whole thing, like the whole sequence, and we now just designate which is conditioning and which is like the thing we want to generate with noise levels. But of course, actually what we're going to do is we're going to just train it with diffusion forcing. So we're just going to add random levels of noise. Okay, so now something really cool happens. Oh yeah, and this is the thing that I just explained, right? The difference between conditioning on the first frame and not conditioning on the first frame is just a question of how much noise you add. If you add all the noise, you dropped it out. You're not conditioning, it's an unconditional thing. And if you have no noise, then it's conditional. Okay, so here's the thing that we came up with. This is kind of neat. So these are the frames you want to generate. So you sample a video sequence from your training set. The frames you want to generate, you add noise to them. And now here's different options for the history. You can either keep the history clean, or you add complete noise to the history, or you add maybe different levels of noise, like you mask out some of them and leave others intact, or you like partially add a little bit of noise to all of them, right? These are just different things you could do with the history. Now you just like put these together and you stick them into your diffusion model, and now basically you get these different kinds of scores. Just as before in the classifier-free guidance plot, you basically now sample from different conditional distributions. You sample from one distribution, which is just the straightforward conditional score of these images conditioned on the history. And this one is clearly the unconditional score. This one is like conditional on those frames, but like not on that one. I don't know what that's used for, maybe something. And then this one is kind of also a weird one. This is like a partial conditioning. And we'll talk about in a moment what exactly you're doing there. And now clearly you can just like take this one, or you can do classifier-free guidance with any of those. You can basically combine, mix and match these different kinds of conditioning variables to basically sample from your model in different creative ways. Okay, so these are the different kinds of guidance. Let's talk about one of them, which is particularly fun. So this one we call fractional history guidance. This one is really cool. This one you're basically, in a simplified way, you're basically asking the model to be more consistent with the partially masked frames, with the partially noised up frames. Okay, what is happening here? This is really fun. What happens if you add noise to an image? Images in the natural world have this interesting thing, which a bunch of smart people have actually written papers on 20 years ago. For instance, Antonio Torralba has a paper on like the power spectral density of images. They have this interesting thing that they have a kind of, a power law spectral density, which means like most of the energy is in the low frequencies, and as you go up, it kind of decays linearly. Now, the interesting thing is that if you add noise to something, so like this is so this is like one of these slices. So this is the Fourier transform, and then as we like move the slice around, this is the plot that you just saw. Now there's this cool thing, right? If you, what is the power spectral density of white noise? It's flat, right? It's just flat. It's all linear. So what happens if we take? I did tell you. I asked you a question. So what happens if you add noise to an image? It's linear. So really, what just happens is you're drowning out the high frequencies first, right? Essentially, it's a kind of low pass filter. But note that it's only a low pass filter if your images follow this law, which not all images do. So it's not always a low pass filter. Right? Okay, but if we add noise, you'll drown out the high frequencies first. So as you're raising the noise level, you'll basically destroy the high frequency information first. Okay, so now what we're doing here is essentially we're doing guidance with blurry history. If we do guidance with these partially noised up frames, essentially what we're doing is we're doing guidance with blurry frames. And now, why is this a reasonable thing to do? First of all, it's a reasonable thing to do because we discussed earlier, it kind of stabilizes the autoregressive rollout, right? Because it basically destroys some of the errors that the diffusion model might have made in generating past frames in the first place. So like, first of all, it helps a little bit in that way. But the other interesting thing it does is when you're blurring during training time as well, when you're blurring out these frames, you're basically increasing the support in the training data for this kind of sequence. Because, right, at the extreme limit, imagine you literally low pass filtered these images. Eventually, they'll just be like the mean of the image, right? And so like now this conditional distribution of this condition on the means that has a lot of distribution, a lot of support in the training data because the means are kind of similar. Does that make sense? Okay, good. And so basically by blurring it out, you're basically increasing the support in the training data. You're basically sampling from a simpler distribution. Cool. And so like this is basically the idea. And so like we call this concept history guidance, guidance with history. You know, like if you just, these are all the same model and just sampled with different ways. So here's the ground truth for reference. And now given the first frame, we're basically just rolling out the video generation. And what you can see is that these videos that are generated are dramatically better than either just rolling out with standard diffusion. Binary dropout is a baseline that is not trained with diffusion forcing, but instead it's always 0 or 1 for each of the frames in history. And this one is not important. So these videos look much better. It's also interesting if you look at these gymnastic sequences, right? Gymnastics famously right now a big problem with these diffusion models. And you can kind of also tell why that's happening. What's kind of happening is that the model mixes a dancer with the person that is doing gymnastics, which kind of tells you a little bit of what the model is doing. The model is kind of, you know, smartly interpolating the training set. And what's happening here is that the model is just kind of drifting into another part of the training distribution because it sees these past frames, and these past frames in the space of the model look kind of similar to someone dancing. And then it rolls out someone who kind of looks like they're doing a pirouette or something. Okay, but the coolest thing, so here's like now real estate in K. So this is an indoor scene data set. And what you see here, these are samples, like 5 different samples given the first 2 frames of the video sequence. And right, it's really cool. So we're starting out with the first frame, and now we're rolling out, and you can see that they're quite diverse, right? So they're really different sequences, and they look quite good. And you know, now one thing that I will add is that I'm a novel view synthesis guy. That's what I worked on a lot with differential rendering. The 2 students that worked on this project do not care about novel view synthesis or multi-view geometry, and nevertheless did much better than anything that I had ever built without even thinking about it. So this is something to reflect on. This completely vaporizes novel view synthesis benchmarks, right? Clearly. So, I mean, okay, so like here's now the really cool thing that we can do. Given the first 2 frames of this video sequence, with the same trick of stabilization and this fractional history guidance trick that we discussed earlier, we can roll out the sequence to up to 1,000 frames. So given 2 frames and a model that only denoises 8 frames at a time, we can basically, in a sliding window manner, just keep rolling out the sequence and generate up to 1,000 frames. Eventually, it still diverges. It looks pretty good. Of course, has some obvious flaws. Like one obvious flaw, if I turn around, the house suddenly looks different. That would is a little disconcerting. And you know, now you could say, oh, we're going to fix this with 3D memory, etc., or you just make the context window longer. Right? Okay. Good. So this was led again by Boyan, and then an undergrad Kiwan, who is also now at OpenAI. There is a pattern. Okay, so now this is kind of the first technical part of the talk. Now I want to go a little bit, take a step back and do a little bit of high-level controversial discussion. Okay, so like this is these are now what follows is a little bit of opinion, and so like please this is more fast and loose, but maybe interesting for follow-up discussions. Yes. Okay. So after we wrote this diffusion forcing paper, there was a startup, Deckard AI. This was October 2024 that just scaled up our model and trained it on Minecraft. And they have this demo, which you can still play today. It's called Oasis. It went viral on Twitter, where you can basically play Minecraft in an AI. there's no, it's just you can play Minecraft. It's an interactive Minecraft game. It's very fun. It has all kinds of flaws, which people thought were very funny. This was in October. Yeah, they raised $32 million with this demo. I didn't raise any money with this demo. So this was October 2024. Okay. Then this was February 2025. This was a few months. Right. So this is pretty cool. Then Google just released Genie in August. This is a few months later. This is also just a video generative model. There's a bunch of other really cool tricks that are being done here to make it real time, to make it action conditional, etc. But fundamentally, it is that kind of line of work. Okay. By which I don't mean I claim credit for this. By which I just mean like there's nothing fundamentally that you don't know about this model. Like you know most of the pieces of this.
How long can you play the game? Like until when that it just goes insane?
So I don't know that this model diverges. It's not public, so we won't know. It might not diverge. There's like several different things you could do, I think, to make it stable. The memory that it has is about 1 minute. So like it's like consistent to up to 1 minute, and you can ask how does that work, etc. But we're not going to talk about that. Okay, so this is like a 1 minute rollout. Here's another example. Is that this part? So this is also just a video game, quote unquote, that is generated from a text prompt in the first frame of this video game. So everything you see here is just generated by this video term in real time, right? So it's pretty fun. So the point that I want to make is, of course, that this is going pretty quickly, and that it's like the kind of the trend is kind of visible. In fact, I want to make the following controversial statement. I think that rote models are just at the beginning of where they will be in 3 or 4 years from now. Like it's a subtle thing, so it's fun to discuss. So if you think about LLMs had like every paradigm always develops on an S curve, by which I mean there's time where it warms up, then it goes fast, and then eventually it like flattens off. LLMs, I would say 2021 with GPT-3. I think that was 2021. I think we were about here. Where do you think are we now? If I would have to, who thinks show of hands that we are here? Who thinks show of hands that we're here? Right, that's what I think. So okay, good. What I will claim is that with this video generative modeling paradigm, we are here. And there's very obvious reasons for this. These models are small. They're trained on very little data compared to what these LLMs are trained on. And there's a lot of money in this. A lot of smart people, like my students, go work in industry to scale this up. It's going to be quite exciting. Okay. So what does that mean? Reflect on this for a moment. What will happen? My prediction is that scaling these models will behave quite like scaling LLMs. And this is kind of weird to even talk about because there's no good way of talking about it. But specifically, I think I will say that they will work as well as LLMs work today in like 3 years, in two years from now. And it's really strange because it's kind of hard to say. But you know that LLMs haven't solved the problem of language modeling. Every time you touch an LLM, you know that it's weird. It makes dumb mistakes. Sometimes it makes no mistakes. But you just all told me that you think we're at the flat end of the curve. So how much better is it going to get? Maybe not that much better. So the same thing I will claim will happen for video models. It's kind of difficult to think about what that means. Like what is the equivalent failure modes for video models? It's hard to say. Some examples of failure modes for LLMs that are kind of well known, and I'm like really not an expert on this, right? But I think just for example, like one problem with LLMs is, you sample them and then sometimes they land at a part of the conditional distribution that is like really weird. They kind of they generate something that kind of fits the prompt, but not really. And then it's impossible to convince them to do something else. Yoon Kim at MIT, who knows this better than me, tells me this has a name. It's called digging in. So like the LLM kind of digs into this part of the distribution and it's impossible to prompt it out of it. They don't know when they're wrong. They kind of, and they are definitely wrong often. And there's an inability generally, I would say, to generate anything for which there wasn't a lot of support in the training data. And the notion of support is kind of difficult to talk about. Like, what is support in the training data? We're not gonna talk about that unless maybe in the discussion afterwards. When is my talk over?
Whenever you end.
Is it 15 minutes now?
You can keep, as much time as you want.
Okay. Okay. Well, okay. So here's some interesting prompts. You might be like, oh my God. Whatever I'm working, we're all going to be like, it's all going to be done. Vision and robotics are going to be done. And there's good news and bad news. The good news is that, yes, start with the bad news. The bad news is anything that you can solve by prompting a video model with images or videos is probably going to be done. It's going to be gone. So if you want to do segmentation, probably gone. Or if you want to do novel view synthesis, it's gone. Don't even, it's like no point. It's done. Okay, you could just wait, but it'll just it's done. Okay, good. So, however, some things are not solved by scaling up these models, and I think that's important to reflect on. The first thing is, what about other modalities? So, what about, for instance, it appears that we can only train these models for modalities for which the data is abundant. What about touch? What about proprioception? What about like weird sensors? The models. There you won't be able to collect that kind of data. So even if we scale up these video models, and even if they work so well at generating video, these problems will not be solved just by making them bigger. And the point here is that I want to make is that it appears that fine-tuning these models, you might say, okay, we're just going to train this model, and then we have new data, new modality, we're just going to fine-tune the model, and then we don't need as much data. The weird thing is that these models don't appear to take fine-tuning all too well. Please keep me honest here. This is the best of my knowledge. It appears that in order to endow the model with an understanding of a different modality, you will just have to collect a lot of representative data for that new modality, and then train it on that. An example for that is, in fact, control. If you think about controlling the camera in one of these models, it appears right now that fine-tuning the model with a little bit of camera data to get control over it does not work. And instead, the way that people are doing it is they collect huge amounts of camera data together with video data. And that is really interesting, and it should raise a few questions. So first of all, if that doesn't work, then what does that mean about the model understanding or not understanding this fundamental aspect of the distribution it's modeling? If it would learn a model of this that is kind of related to the physical model, it should take fine-tuning really well, but it does not. And there's ways around this, which we're going to talk about in a moment. But yeah, this is an interesting thing. Then extracting actionable information. We're going to have a little case study on this. Okay, so here's a case study on robot planning. Let's say I want to ask a robot to pick up a brush that is lying on a table. I have this picture. Imagine this was a robot hand. Right now it's a human hand, but it could be a robot hand. And now I want to make a plan for how to pick up this brush with this robot. 10 years ago, how would we have done it? We would have estimated the point cloud, then we would have done segmentation, then we would have done the grasp generator, then we would have done planning, task and motion planning, blah, blah, blah. And then it would have still not worked in the middle. Unless you already know the brush and you know the table. Okay? Good. Now what we do is we ask our video model, please pick up the brush. That's neat. Okay. So the model just generated a video of us picking up this brush. Now, this is great. Here's another example. Close the laptop. That's neat. I didn't have to tell the model how the constraints of this laptop, the mechanical properties of the laptop, the force involved, blah, blah, blah. This is great. This is really solving a big chunk of problems that we have in robotic planning. It's really awesome. Of course, at the same time, seeing the constraints that we just discussed, okay, I give you this video, now what? What are you going to do with this video? You still have to execute it on the robot. And the model isn't telling you what actions you have to execute on the robot. So that's not great, right? So I guess what I'm saying with this is you don't want to underestimate this development. This is going to work for pretty much anything in the not too distant future. In 3 years from now, I can take a picture of you and I'm pretty sure I can tell it this guy is standing up and leaving and it's going to work. Okay, it is pretty neat, right? At the same time, still clearly problems left to be solved. What are you going to do with that video? There's still a lot of interesting questions here, right? Okay, let's talk about one question. Control. We want to build a model that you can sample by controlling the camera. You want to be able to control the camera and walk around in this thing. Does that make sense as a problem? Yes, great. Okay, so here's something that is kind of self-deprecating. There's a discussion we had many times today with the students, which I really appreciated. One thing you might say is, okay, maybe, so first thing is we need to do this somehow at scale. We need to do it self-supervised. We can't just collect a large data set of camera poses and then train the model with that. Maybe for camera poses that works, for other things it doesn't work. So we want to do it self-supervised. You might be tempted to say, well, we know how camera poses work. We know how the 3D world works. What if we use our understanding of the 3D world to build a bunch of inductive biases and multi-view geometry constraints that basically allow the model to reason about camera poses, etc. I personally have worked on this a fair amount. This is the kind of set of techniques you might think of: novel view synthesis, NeRFs, camera pose transformations, duster, cost volumes, feature matching, scene flow estimation, you name it. The classic multi-view geometry toolbox combined with deep learning. I have thought for a long time that this might be a way to solve this problem. Today, my opinion is that this is not a way to solve this problem, and that any attempt of combining multi-view geometry with deep learning is doomed to fail from the start, and you shouldn't attempt it. It is a waste of your time. Certainly, it was a waste of my time in some way. Right? I'm over exaggerating for comedic effect, but right, like, so this is really just the bitter lesson, right? So everyone knows about the bitter lesson. My bitter lesson, personally, was that not only are the inductive biases of the model, like the kind of structure you built into the model, kind of questionable, even the whole assumption of doing 3D reconstruction is questionable. In this framework of embodied intelligence, right? If you're working on medical imaging, on like, it's completely different thing. I'm talking about the case where you have robots that walk around the world, they can collect lots of data, self-supervised, we have lots of samples of this data. In this domain, my claim is that if you're working like me for many years on this problem of combining 3D inductive biases, multi-view geometry, 3D reconstruction with deep learning, you're wasting your time. This includes things like Duster or BGT, which I'm a huge fan of. They are interesting for many reasons. But like, ask yourself, I give you a perfect point cloud reconstruction of this room. Great, what are you going to do with it? Why do I care about a point cloud? It is kind of a historical artifact that the vision people care about point clouds. There are some applications for geometry and depth, but really many of the motivations come from robotics. If you look what the roboticists are doing, it doesn't have anything to do with point clouds anymore. That ship has sailed. Like SLAM and that part's kind of going away. Manipulation also not that much to do with these point clouds anymore. So the interesting thing here, and I fell prey to this myself, is that the vision community has taken this problem, which originally was well motivated, but the application for it has long moved on, but we have held on to this benchmark. But the benchmark actually doesn't make much sense. There is no point to it. Very controversial opinion, right? So like, there is of course nuance to this, which we're skipping. So I would be happy to discuss it with you, of course, right? Just, I just want to make you think about this because I think it's valuable. Okay. Here's a case, yes.
Maybe I'll say something. So I buy it, but my question here is, what's the goal, perhaps? So
great question.
If every living organism survives without multi-view geometry, right? So obviously that's not necessary. Right?
Yeah.
In fact, yeah, it's like it makes no sense. But again, it really depends on what the goal is. So you're not going to be able to build this building, with a video model, right? You can't just do next view prediction and expect to get an actual 3D structure built. So I totally agree that for the task of surviving under absolutely any condition and being robust to whatever nature throws at you, you do not need that.
Yeah.
But our world is not quite just that.
Yeah, I agree. So what you just, I think, did, and I 100% agree with this, we found an application where the 3D reconstruction is inherently valuable. And I think that's totally fair, and that is a good motivation. My motivation is building embodied intelligence, as you say. And you're saying, like, obviously we don't need multi-view geometry for this. I think you're just smarter than me. I did not, me and I think many other people did not have that initial reaction. Or while we might have agreed with that even like 5 years ago, what I would have told you is somehow still lies on the critical path towards building systems that do that without having these inductive biases in the end. And I think neither of those two is true. I think you're right that there are applications in construction. At the same time, right, there's a lot of people working on this research problem. Is that validated by the value of like construction? Maybe not. And also for construction, we don't do 3D reconstruction actually. We do CAD, which is a completely different thing. So actually, I think there are definitely applications for it. It would, I don't know that there is enough applications for this problem for us to have 15,000 researchers send papers to CVPR on 3D reconstruction. But I agree with the general statement that you can definitely find applications for which this remains an important problem. And as I say, no shade, BGT is an amazing paper. I'll encourage you to read it because there's other things to take away from it than the benchmark. And there's other things you can learn from it. And I read it and I'm a big fan. But I will still say that maybe the authors themselves, you know, I haven't had this discussion with them. I don't know if they would agree, but I think it would at least be an interesting discussion. But yeah, thanks for the comment. Yes.
Sorry, this may be a bit too much into the future, but I'm wondering mainly if we do get like a black box system that predicts like that can model in embodied cognition the next steps to take, or like allow an embodied cognition robot to survive in the real world. I'm wondering if we cannot access geometry from it, like explicit geometry from it, to what extent do we actually understand the network, or are we just back to the black box problem of like neural networks?
It's a good question. I think we are, for now, I think the answer is that there is no interpretability aspect, or like no interpretability method that I have seen provide significant insight into what these models are doing. Not for LLMs, not for video models. I think that would be amazingly interesting to study. I have attempted it a few times and have since given up. I think the thing that is, I think, interesting, maybe one thought for interpretability, I think the mathematical toolbox to study the interpretability of these models is tools that I think very few people in this room are familiar with. And these are really, you know, like the one of the papers that maybe would go in this direction roughly is like neural tangent kernels. Because really you are asking questions about the performance of these models outside of their training samples. And those are unfortunately incredibly mathematically general statements about this machine that we currently do not have I certainly am not aware of anyone who has a good approach to approaching this. And I certainly don't. I wish I had. I have no clue. But yes, interpretability is super important. I think you will probably, if you can solve this problem, I think it would be a huge problem. But right now, I'm not aware of any approach. Great question. So I think we're for now stuck with the black box. Yes.
So you said like multi-view geometry maybe was like actually a hindrance towards our final goal, maybe of like embodied intelligence. In the same sense, if we take like inspiration from humans, maybe.
Yeah.
I don't think I'm doing photorealistic next frame prediction either. I'm probably maybe doing it in some feature space or something. That's why I'm surprised when I see something random happen. But then maybe this is also actually a futile goal. It's something that's actually hurting us towards this goal. And maybe you'll look back on it a few years later and also be like,
in fact, I'm already looking back today. And like I'm thinking about this today, and to be fair, lots of people are thinking about this, right? This is this whole line of work on like, you know, JEPA or, you know, like alternatives to generative modeling. And yeah, I would totally agree with that. And I am working on other kinds of approaches that are not generative modeling based.
I see.
And I think this question of, you know, the difference between these methods is a very interesting one. So I think, in fact, I think you are raising a great research question. Cool. Let's move on. This is just the most painful recent experience that I've had in this line of work, right? So the reason why I pitched this so emotionally is because I recently fell prey to my own biases again. Let me tell you how. I was interested in the problem of self-supervised novel view synthesis. I've been interested in this problem for a long time. The novel view synthesis is not the important part. The important part is, can we discover the notion of camera poses self-supervised from data? We basically want to discover this important piece of structure of video, which is the motion of the camera, self-supervised from data. The first thing I will do is I will tell you that any new novel view synthesis algorithm looks like this, is they all are instantiations of this general framework. You have, let's say for now, we're doing single image novel view synthesis. You have a pair of frames like this one and this one. When you train the model, what you are essentially doing is you take these pair of frames, you give them to a pose estimation model. That pose estimation model gives you some representation of the camera motion between those two frames. And then you take the first frame of those, and as well as the pose, and then you ask it to render the second frame. Does this make sense? So in fact, you know, of course, if you think about things like, novel view synthesis with poses, those are just like the pose encoder is just common. It's like a handcrafted, expert-crafted way of extracting this like handcrafted pose variable from it, and then you're just training it end-to-end. There's another line of work which is really exciting, which recently there's this paper Razor. Who's heard about Razor? Okay, it's really cool. You should read it. It's amazing work. There's another paper called Rust from Google, and then I have also written a few papers on this FlowCam and FlowMap, which basically try to build versions of this that are just end-to-end trained. Like basically, we don't assume that we have a handcrafted model for estimating poses. We try to train some version of this pose estimator from data. Does that make sense? Okay, that's a problem statement. Yeah, these are Razor and Rust, and these are really cool. And let me give you a brief idea. So these slides are completely new. So if I'm scatterbrained, excuse me. So the way that Rust works is essentially you take a bunch of images, you encode them, then you take a training time, the image that you want to render, you take half of it, and then you basically have a pose estimator that gets half of that image as well as all the context images, estimates the latent pose, and then you give that to the renderer. So it's just like, it's exactly an example of this architecture that we just discussed. Okay, so it turns out these models have made pretty cool progress. So this is this paper called Razor. So this is from Hanwen and Hautan from George's Pavlakos group. Fantastic work, really inspirational. It's really good. So here's LVSM. So this is kind of a supervised baseline with poses, and then this is the method that they show, which is like the self-supervised method, which is not trained with camera poses. And their claim in the paper is that this method really improves on the supervised baseline. However, it turns out that the thing that you're seeing here is an example of an autoencoding thing. So what you're doing here is you're taking this video sequence, and then you're using the model that you trained to estimate the poses from that sequence, and then you're just re-rendering the same sequence with the poses that you extracted. So this is the result that you see. And this is where you can get a big improvement over the baseline. However, what we realized while working on this project is what actually matters is the transfer between scenes. And let me say what I mean by that. What I really want to do, and I can tell you in a moment why, what I really want to do is I want to take some kind of video sequence, I want to extract the poses from that sequence, and then I want to use these poses to render a different sequence. That's what actually matters, and I'll tell you in a moment why. And it turns out if you try Razor or Rust on this problem, it doesn't work. You can extract the poses from this video, and then try to re-render this video here, and what you'll find is that it just renders completely different poses. Even though these poses, note that these are parameterized for Razor as SE3 variables. So like essentially the model predicts like little rigid body pose transformations. It doesn't work. And same here. So this is another transfer from like this scene to this scene, and it doesn't really work. And so the thing that is interesting is that Razor has a 3D inductive bias. It parameterizes the camera poses as SE3 elements, as rigid body transformations. And the interesting thing to realize is just because they are SE3 poses does not mean they behave like SE3 poses. Because at the end of the day, they're still being interpreted by the renderer, and the renderer can do whatever it wants with these SE3 poses. And so the interesting thing here is that this is not actually a novel view synthesis algorithm. This is failing to do the basic task of novel view synthesis. The basic task of novel view synthesis being giving you a way of, given a set of images, render a specific pose that you defined. That's the whole task of novel view synthesis. If I can't have a way of, in a generalizable way, specifying the pose, it's useless. It's just like video generation then. It's like frame interpolation or something else. You need this control over this pose. And now, of course, you could go and you could say, well, it turns out you could try to do this with COMAP, which doesn't have this problem. You can expert craft this thing. And that's what we tried to do for a long time. We tried to build all kinds of inductive biases, etc. First, let me introduce a metric by which you could measure this property. We call it the true pose similarity. Any novel view synthesis model, what you're going to do is you're going to have the frames from which you estimate the pose, then the scene that you want to render, and then you're going to render this scene with these poses. And then you can just use some kind of oracle like COMAP or like VGGT to extract the poses from these two sequences. If the poses are the same, great, your method is transferable. If the poses are not the same, like what we just saw, then your method is not transferable. And it turns out transferability is actually the same as controllability. Like the ability of specifying a view is identical to this property of the poses transferring between scenes. It is the same thing. So, and why that is maybe a little bit more subtle. I encourage you to go to the paper, but I think intuitively, I hope it makes sense. So like intuitively, the way you can see this is, for instance, the way you could control these poses at the end is you can just take a graphics engine, you render any trajectory you want, and then that's how you control the poses. And then if they transfer, clearly it's controllable, right? So like just in terms of like checking, syntactically it makes sense, right? Okay, good. So it turns out that this is all you need to define novel view synthesis as a problem. You do not need to make use of any, right? Even this oracle, where we rely on like a way of specifying ground truth poses, is just a crutch to measure this. Really, novel view synthesis is just about this input-output behavior. It has nothing to do with multi-view geometry. It has nothing to do with camera poses. It has nothing to do with 3D. That is what it is. Yes?
Well, I guess the question here is again, what is the goal, right? Because if you're so pose estimation is sort of completely agnostic to what the input data is. This goes back to what you said earlier, right? It could be radar, it could be points drawn by somebody, it could be camera output, it could be a bunch of different things.
Yeah.
So the underlying geometry is the same in all of them. Of course, you can express this input-output mapping, but then you're locked into a particular modality. Let's say images, color images from the camera, as opposed to other kinds of data.
I'm not sure why would you be locked into a different modality. So let's say you have the same for radar. I think you could define a similar property for radar. No?
But you'd have to train it for that, right?
Yes, you would have to train it, but you would have to train the model that is conditional on camera poses anyways, right? So that is the same between both algorithms, because the renderer has to be trained for that modality anyways, and the pose estimator is also handcrafted. So the only thing we have done is we have fixed the camera pose representation as like a human-defined property, but I think that the algorithmical challenge to me seems like it still remains. And actually, you can also define a transfer between radar images and RGB images. I think you are free to do that. And I would, in fact, I would claim that if it is indeed true that both of these things are rigid body transforms, then a transferability property like this will always exist. Do you think that's fair?
Probably.
We have to think about it. But interesting question. So there's a question of modality. Okay, we're over time already. I'm going to wrap up about this project, right? So I'm going to skip over this part. Let me tell you what the solution was. Okay, I'm going to tell you what the solution was. And let me highlight this again. I worked on this problem for 4 years with all the most complicated math that I have ever done, which is not a very high bar, but nevertheless, I really got into equivariant machine learning, geometry. I tried to constrain the latent space in cool ways, like parameterize the Lie group, predict things, everything you can imagine, everything up and down. And then I went to a talk of Mathilde Cornet, who's the first author of Dino, and I felt like a fool because I watched her talk through the research that she has done, which is very impactful, and not mention forward modeling or physical modeling a single time, and just thinking only about information. She was only thinking about what do I have to give to my model? How do I have to supervise my model to get the thing that I want? And then I was frustrated, and I felt well, this is super cool. I went back to my office, and I was like, okay, what's the dumbest thing I can do that has nothing to do with geometry and that still has a shot at solving this problem? And guess what? It worked. Okay, here's how it works. You take your input pair, you apply a data augmentation that keeps the pose intact. So here we are essentially, one option for this is masking, another one is random cropping. You generate 2 non-overlapping random crops of these 2 video sequences. Then you apply color augmentation, whatever you want. You give this pair to the pose estimator. You give this first image to the renderer, together with the pose that you estimated, and you render it. Okay, good. And then you supervise it with the other crop. Why does this work? It works because the only information that these 2 have in common, if you did a good job at augmenting the pair, is the pose. They don't have any overlap in pixels, and it's very difficult to predict the content of a random crop from one other random crop. That's very difficult. So that's not going to happen. So what is the model going to share? What's the information that the model can share? It's exactly the camera pose. And in this way, we were able to not quite solve the problem, but do dramatically better than the baseline. So here you see now the synthesis. We're in fact transferring the poses from this video to this Code3D video. And these are the poses that we're extracting. And you can tell that Razor and Rust don't do such a good job at it. And we are now doing controllable novel view synthesis, because we can, of course, choose this video to be anything, and re-render this thing without ever using any concept for multi-view geometry at all. Here's another example. The blurriness this is not a generative model, it's not a diffusion model. The blurriness is a sign of uncertainty. So extending this into a diffusion model is interesting. So this is the worst it'll ever look. But appreciate that this is one scene, and we are transferring the poses to this. And instead, what Razor and Rust do, even though they have this 3D inductive bias, Razor does, they render other poses which have nothing to do with the input view. So there's other examples for this, but I think you get the idea.
The bottom is from Colmap?
The bottom is from VGT, in fact. So like we extract the poses with VGT, which is not perfect because of course the views are blurry. So like, VGT is surprisingly robust, so I'm grateful for that. It's a great paper, you should read it. Okay, here's another example which I thought was cool. And there's an interesting thing here where there's scale ambiguity, right? Like what scale are you generating is a very interesting question. Okay, and now we're way over time, so I'm going to wrap up. There's a bunch of more slides. You can also train a probe, like representation learning style, where you take the latent and you predict the pose from it, and that works really well. So you can imagine that this is a self-supervised way of pre-training a pose estimator, and then you can fine-tune it to predict the pose parameterization of your choice. So this is a really cool, exciting direction. I have a whole other project which I won't talk about, because I think we're out of time. But it's about learning learning a controllable model of your body by watching yourself move. It's very exciting. For now, I think I'm just going to wrap up. Thanks so much for your attention and for engaging. I really appreciate it, and thanks for inviting me. And yeah, talk to you soon.